Let's assume, for the sake of contradiction, that the square root of 2 is rational. This means that it can be expressed as a fraction in its simplest form, where the numerator and denominator have no common factors other than 1. So let's say that the square root of 2 is equal to a divided by b, where a and b are integers with no common factors other than 1. Now, square both sides of the equation to obtain 2 equals the quotient a squared divided by b squared. Now, multiply both sides by b squared to get rid of the fraction. 2 times b squared equals a squared. This implies that a squared is an even number since it is 2 times b squared. Now, let's consider a. If a is even, then a can be expressed as a equals 2 times some integer k.
Taylor, I think you're forgetting to show some working, Taylor. You're not forgetting that mathematics requires rigor, are you, Taylor? Taylor, tell me this. Why should it hold that a is an even number? You've only shown that a squared is even. But what about a, Taylor? Why, Taylor? Why must a be an even number, Taylor? Well, don't worry. I'll tell you. It's because if a isn't even, then it must be odd, in which case it is easy to show that a squared must also be odd. And since we know that a squared isn't odd, then it follows that a is even. Now that wasn't so hard, was it, Taylor? The Taylor, make no mistake, just because this working was easy, Taylor, doesn't mean that we can omit it, Taylor. Because if you did, you might end up with a whole planet of maths teachers who believe they can swap this 2 with a 3 or a 6. But this step, Taylor, this step that you omitted, Taylor, it doesn't generalize like the others. A whole planet of maths teachers, Taylor. A whole planet of maths teachers teaching an infinite set of flawed proofs. Also, I hate to say it, Taylor, but the proof you have here only shows that no rational number whose square is 2 exists. It hasn't actually shown the existence of an irrational real number whose square is 2. So you might want to clarify that one too, Taylor.